at the top of section 2.1 as well. AN xn, AN minus 1, xn minus 1. And then that pattern continues. So the pattern of the exponents, they just descend in order. And it goes on until we get down to the last power, which would just be to the first. And then the last term is a constant. So a polynomial has to have positive, and I should put on in here as well, whole number exponents. So positive whole number exponents. Every polynomial has to have positive exponents. They must be whole numbers. So I can't have x to the 1/2. That's not considered a polynomial. Or x to the -2 is not considered a polynomial. So underneath characteristics, just a couple of characteristics of the graphs. So these graphs are curves. And I could have multiple curves. So think of like the hills and the valleys. We could have a couple of hills and a valley, but all the graphs are curves. There are no breaks in the graph, which means the graph is continuous. And our graph will go on forever. So that's the other word with continuous. The graph continues to go on forever. So we have these smooth curves without any breaks, without any gaps. It's continuous, it goes on forever. Underneath that, it talks about the most basic type of polynomial, and those are called parent functions. So the most basic type of a polynomial would be if I just had x to some type of power. So think x squared, x cubed, x to the 4th, x to the 5th, x to the 10th. All of those are basic because they have nothing after them. So that is why we call it a parent function. Parent functions are basic functions. There are two different pieces underneath here. Every basic polynomial meets these properties. So if the n, the exponent, is even, so think your x squared, your x to the 4th, your x to the 8th, the graph touches the x-axis at its x-intercept. That is a property of every even-powered polynomial. And we're going to have to use these properties to help us graph. So x squared is our famous parabola. And it touches the x-axis at its x-intercept. It doesn't go through the x-axis, it touches it, and then it continues on. So it's a decreasing curve at its x-intercept, it continues up the other direction and becomes increasing. Every even function does that. So even if it was x to the 100, it's still going to touch the x-axis at its x-intercept. The other option is odd, because I only have two types of functions, or two types of powers, even versus odd. So when it's odd, it says the graph crosses the x-axis. So instead of just touching it, it's going to cross through the x-axis. What's our x cubed graph look like? Yeah, nice job, Brenton. So that graph that goes up and down from the center. So if it's an odd power, the graph crosses through the x-axis and then continues on. So even power, it touches and moves like the opposite direction. It was decreasing, now it's increasing. Odd graphs continue through the intercept and continue on. So it's still an increasing function. This increasing function goes on forever. So increasing from negative infinity to positive infinity. So those are two properties that we'll think about when we try and graph. So even functions touch the x-axis, odd functions cross through the x-axis. So if you look at the 3 graphs underneath, see if you can just sketch these first. We'll worry about the end behavior. If you need to look at your calculator, you can take a peek at your calculator, but we have negative x to the 5th, x squared, or x to the 4th plus 1, and then in the parentheses, x plus 1 to the 4th. So just graph them. And then we'll talk about what the end behavior means and how we're going to describe that. A lot of your homework tonight is just describing end behavior. So it's like once you kind of see what it means, it's really easy to describe. You will need your calculator, so you can pull it out, take a peek at it. So the first one says y equals negative x to the 5th. So Josh, what did that look like, negative x to the 5th?
It's across over the x-axis.
Yeah, it crosses through the x-axis. And is it an increasing or a decreasing function from left to right?
Well, I mean, from left it's decreasing.
Yeah, so it's decreasing. So if we look at that negative, the negative makes it go down the whole time. So on the left, it looks like it kind of like flattens out in the center, and that's just because of that large power of x. But it's decreasing the whole entire time. So then it says to describe the end behavior of the polynomial. What do you think the end behavior would be, Colin? Where it ends. So usually we are so focused on what's going on in here that we don't really talk about where the graph ends. But a graph actually ends in 2 places. Technically you would think, well, that's where it begins. And over here is where it ends, but both pieces are considered the end behavior. So where does the graph end? And we always describe where it ends on the left and where it ends on the right. So to start off with, I'm going to just do like basic verbals, more English kind of sounding instead of math. But I would say the left side goes up and the right side goes down. That would be describing where it ends. So on the left side, it's ending up. We could even say it's ending up at infinity. The right side is ending down, and it's ending down at negative infinity. That would be the end behavior, the non-mathematical way to describe it. So the right side goes up, the right side goes down, the left side goes up. And that's because there's a negative in front, and it's an odd power. So then looking at B, Dylan, what is going on with B, x to the 4th plus 1? It is a parabola, and it moves up 1. So it moves up 1. The only difference is the parabola is a little wider. Again, it's because it's a larger power of the 4. But still a parabolic shape. So describe the end behavior. Emma, what would you say the end behavior is doing? Yeah, both sides are going up because it's even. So even, both go up. They do the same thing together. So we would say the left goes up and the right goes up. Again, that's end behavior. So when it's even, they both do the same thing. When it's odd, they split. One goes one way, one goes the other. So then letter C, we have in parentheses x plus 1 to the 4th. Garrett, how's that graph moving?
Oh, it's moving left 4.
Left.
Left 4 is basically.
Ours is different.
Oh, you have a 4. Okay. Sure. Left 4, sorry Garrett, I apologize. And it still has that kind of parabola looking curve. That parabola looks kind of crappy. But you can see that it's not really changing the end behavior. Yeah, it changed the intercept, but the end behavior is still the same. So the left would go up and the right would also go up. So that would be end behavior. Where is the graph ending? There are 4 different options underneath this, 4 different cases for end behavior because it depends if it's even or odd. And it depends if there's a negative sign in front or if it's a positive sign. So we're going to just try and do a little summary so that we can kind of represent each case of the end behavior. So the first one says we have a polynomial of an even degree. So any polynomial of an even degree. So x squared, x to the 4th, even like x to the 20th, as long as the power is even. So when you're looking at a polynomial, the one thing we're going to focus on is the power. The other thing we'll focus on is the leading coefficient. The leading coefficient is the number in front of the biggest power, whether it's a 1 or 2 or 7 or a negative 8. So leading coefficient is the number in front of the largest power. And we have the option of it being positive and the option of it being negative. So leading coefficient, if it's positive, that means I have a problem like y equals x squared. All we're worried about in this is just the end behavior. So any coefficient that is even and it has a positive with that power, so a positive 2, a positive 7. The end behavior, the end of the graph, and I'm not drawing the rest of the graph, I'm just drawing where it ends, both end up. When we describe end behavior, we are going to describe it in a more algebraic way. So we're going to say as x goes to negative infinity, that means I'm on the left side of the graph. So as x is doing this, what's the y of the graph doing? So if I'm on the left side of the graph, where's it going? Lauren? To positive infinity. This is the algebraic way, the mathematical way to describe end behavior. So as x is going to negative infinity, the y is going to positive infinity. As x is going further and further left, my y is going up. On the other side, we're going to kind of state the same exact thing, but now we're on the positive side of infinity. So as x goes to positive infinity, Lauren, what happens with the y? It also goes to positive infinity. And that's because it's an even function. And even functions perform in the same manner on the left and the right. They both go up or they both go down. So end behavior is describing the end of the graph. Where does it go? We know it's going to infinity because it's a polynomial. But what side is going to positive infinity? Which side is going to negative infinity? So if you look at the next one, still an even coefficient, but now it's negative. So I'm just going to place a negative in front of that. And draw a little graph. Even means both sides go down instead of both sides going up. So see if you can write the end behavior. So start with the left side. So negative infinity is left, positive infinity is right. Always thinking first in terms of x. Hannah, if x is on the negative side, as it goes to negative infinity, the y goes to negative infinity. And as x is on the positive side, positive infinity, y goes to negative infinity. And again, that's because it's even, so both of them perform in the same manner. So that would be our end behavior. So if you haven't already, looking at the odd degree, so So we could have x cubed versus negative x cubed. Just draw the end of the graph because we're worried about the end behavior. And then write a little statement to represent the end behavior of your graph. So a positive odd power versus a negative odd power. There can be a whole bunch of stuff going on in the inside, but we're looking at that end behavior. So Colin as x goes to positive or negative infinity on the left side. There we go. Y is going to. And then on the right side column, as x goes to positive infinity, y is going to positive infinity. So these are opposites. One goes down, the other goes up. When it's a negative coefficient, it should do the opposite of the graph on the other side. So if you're on the left side, it's going up to positive infinity. And if I'm on the right side, it's going down to negative infinity. So the goal is for us to be able to look at the largest power and the number in front of it. So largest power and number in front of it, those two things. And without using the calculator, be able to describe the end behavior. And there's 4 conditions. It'll only be one of these 4. So on the next page, it does say to use the leading coefficient test, which really means think about the 4 cases of end behavior. Determine the right and the left behavior of each graph of the polynomial. So we're going to try to do this without graphing, and then you can take a peek at the graph using the calculator just to see what's happening. But the leading coefficient test says to go to the largest power, and that would be x cubed. So it's odd, and it has a negative in front. That's the only thing that matters when we're trying to get the end behavior. Odd power, a negative in front of it. So draw yourself just a little sketch. Where's the graph going to end? And then see if you can describe that. So Brenton, if it's odd and negative, what would the graph look like?
It's going to be going up this way on the left side.
Yeah.
It's going down.
Perfect. So up on the left and down on the right. It's going to do other things in the middle, but that's the left and the right. So then we would say x goes to negative infinity, y goes up to positive infinity. As x goes to positive infinity, y goes down to negative infinity. And that's all end behavior is. So describing the left side of the graph, describing the right side of the graph, based off of the largest power and the number in front of it. So the next one, we have x to the 4th, which is even, and there's positive number in front of it. So Josh, when it's even and it has a positive number in front,
As x goes to negative infinity, y goes to positive infinity.
so that's this side.
As x goes to positive infinity, y goes to positive.
Nice. So both sides go up because of it being even and positive. That's all end behavior is. Most of the homework is focusing on end behavior. Questions so far? So can you look at an equation and decide the end behavior? That's part of graphing without the aid of the calculator. The other part that we're going to start today, because you won't actually be doing any graphing, is to talk about the zeros of a polynomial. The zeros are also known as the x-intercepts. So a 0 and an x-intercept are the same exact thing. So a zero of a polynomial, it says it can have at most n real zeros. The power of the polynomial tells us how many zeros or x-intercepts the graph has. So if my power is 4, I should have 4 answers. That's what this really means. I should have 4 x-intercepts. If the power is 3, I should have 3 x-intercepts, or 3 answers, because I'm solving for x and I need to solve for each one of those x's. The second bullet underneath says it can have at most n minus 1 maximum or minimum values. That's the number of curves in the graph. So if I have a power of 4, I have 3 curves in the graph. If I have a power of 3, I could have 2 curves in the graph. A curve would be a hill and a valley. So that power, now I know how many curves I have and how many answers or x-intercepts we should have. The other part underneath there talks about equivalent statements. Equivalent means what? It's another word for equivalent. Equal to, the same. So these statements are all the same, it just kind of depends on the wording, what the question is asking for. So it says that x equals a is a zero of the polynomial. So if I'm trying to find a zero, I can have it as in the form x equals 5, x equals 10, x equals 15. The second bullet, it says x equals a is also a solution of the polynomial, because I'm solving for the equation when y is equal to 0, or when f of x is equal to 0. The third bullet says x minus a is a factor. So if I have an equation with, we'll say, x minus 4 and x plus 5. These guys are factors. If I solve this and set it equal to 0, I now have a solution, or I have a 0. So depending on what the question is asking for, find zeros, find a solution, it means solve for x. So a factor you use to solve for x. The last part says if it asks for an x-intercept, that's when we would take these and write them as ordered pairs. So the goal here is for you to understand, based off of the terminology, that's how your answer should be represented. So an x-intercept is an ordered pair on the graph. It's also the same as a 0, just written differently, or a solution, and it's found from something that's factored. So those 4 things mean the same thing. It just depends on how you're asked to express your answer. So if I'm expressing my answer as a factor, I'm not solving. If I'm expressing it as an intercept, I'm writing it as an ordered pair. So we are going to do just the first part of the bottom questions. And that first part says find all the real zeros of the polynomial algebraically. Tomorrow we're going to talk about the end behavior, graphing it, getting a maximum in, trying to sketch as much as we can without using the calculator, and then we're going to be forced to use the calculator a little bit. So if I have this function x to the 4th minus x cubed minus 20x squared, and you're asked to find a 0, that means I'm solving this when f of x is equal to 0, or my y is equal to 0. How would you solve this? How would you find x? Colin.
Would you set the equation equal to 0?
So set it equal to 0. And then what else would we have to do?
Solve for x.
Huh?
Factor.
Yeah. What can you do to factor this, Colin?
Pull out an x squared.
Pull out an x squared. And then we have x squared minus x minus 20. And then what else would we do, Colin?
You could set you could factor the inside into well, you could complete the square.
We could complete the square. Yeah. Or we could just factor it. What 2 numbers multiply to be negative 20 that combine to be negative 1? 4 and negative 5. So then I could continue to factor this, placing in parentheses a positive 4 and a negative 5. Factoring is a great way to find x. And then my solutions find all the real zeros. So this one here gives me a negative 4. This one gives me a positive 5. The first one, where that x squared, if I set that equal to 0 and take the square root because we're solving for x, technically that answer is plus or minus 0. Do you ever say plus or minus 0? No. But we do say that something special is happening here. And we call this a double root. A double root is saying that that 0 is listed twice. Because I'm supposed to have 4 x-intercepts. Because my power is 4. 2 of them happen at 0, and tomorrow graphically we'll see what special thing happens there. And then I have one at -4 and one at +5. But this has to be kind of notated in the answer because that 0 is special. There are actually 2 of them. So looking at the last one right next to it, we're going to do the same thing. We're just going to do the first part. So this is part A, where it says find the real zeros of the polynomial. So set it equal to 0. Reese, what would you do to factor this one? What could we do?
You take out a -2x squared.
And then you would have,
X squared.
good. How could you further factor it? How would x squared minus 1 factor? Reese, do you know?
X plus 1, X minus 1.
Yeah, x plus 1 and x minus 1. So my zeros, I have a -1 and a +1. And then this guy again, because it's x squared, that gives us a double root. So the majority of your homework is determining end behavior. The last 3 or 4 questions of your homework is just factoring to find the zeros. Hopefully it's a pretty straightforward homework assignment. Have an awesome day. Little quiz tomorrow on those quadratics.